So for the ones who are not able to join today, so what I did earlier was like a basic recap of what we did last week. And this is also actually a recap, but I'm going to actually couple this with the state feedback control, right? So that's why I'm going to derive this kinematics part. So say there's a mobile robot. So I discussed about the, the center of rotation, right? So center of rotation is simply the concept is that say there's a robot like this, right? There's a robot like this, and suddenly the robot wants to turn, right? It wants to turn. And by the time it starts to turn like this, or say it wants to turn like this, and this is actually one time step, right? So in discrete time, I said that basically if the time is going like this, we'll take this is the time, say some say y-axis is simply any scalar quantity, right? It can be any scalar vector quantity, it can be velocity, displacement, amplitude, anything, right? So in continuous time, we can map this, in a continuous way, right? So this continuous, I think I have done this for maths. But in discrete time, we take time as a discrete quantity, right? So we take time steps. So this is 0, 1, 2, right? So 3 goes on, and maybe it can be, represented as Tn. So n is actually the number of steps, right? So in that case, actually, we take this particular time, the value, we sample this, and we just take the particular value at this particular time, right? So this is how discrete time works. So here also, we are actually considering a discrete time interval. So say this is t equals 1. This can be t equals 2, right? But simply for general, for like in a general sense, because we are not considering discrete time here, I will just put this is t equals t, and this is t equals t plus dt or delta t, right? Whatever you want can put. Okay. So this dt component is like a small time, and in that particular time interval, if we like say, okay, this robot is moving in this direction, right? So if I draw, like say, I can draw a normal to this robot's axis like this, right? Like this, and that's the center. If I draw normal to this, like this, and also at this particular point, if I draw a normal like this, my drawing is not very accurate today, but just if you can't understand anything, so basically there's a robot like this. There's the center axis like this, and I'm drawing a normal or a perpendicular line to that, right? These actually meet at this particular point. This we call the, basically it's like a momentary center of rotation, right? So it's momentary, like it's actually for this particular time interval. So basically dt time interval, because you reduce, if you like subs, like, like deduct this from this, you get dt, right? So is it for this for like a dt interval, right? So so in that interval, there's this MCR. So I think you get the idea of the MCR, right? So then what I'm going to do is for this robot, if you can't understand anything, just point it at that point itself, and I can basically explain it again. If you want me to explain singly, also you can let me know, right? So this robot is going to turn like this. Say like this, and at this particular instance, we can get the MCR by drawing this. We'll just assume that it's somewhere around here, right? For the time being, not it's going to be. It's not. Okay, somewhere around. I just assume that this is perpendicular for the time being. Now, this angle I can get as beta, right? Still, actually, this has to come a bit down, right? This actually, there should be another. So anyway, I will just draw it like this. So this is actually the line that is perpendicular to x, right? So I think you can get it. So I will explain this once I have finished sketching. So this is actually the line parallel to the y-axis. Okay. This actually I will draw again. This is the line perpendicular to the x-axis, right? This is perpendicular to this. Just for our, these are like constructs for our reference, right? And this angle is beta. So this we take this angle as beta, right? Now this angle is, I draw this from blue, if not you will get confused. For a better diagram, you can refer this thing, right? I just want to explain the geometry here, but this is the beta angle, right? So you like say the robot is turning like this. The momentary center of rotation is here. And if you point two lines from the MCR to the center of the robot, so basically we are taking a point of the robot, right? X1, Y1 is like a momentary point of the robot. If you just draw two lines, X1, Y1, X2, Y2, to these points, if we draw two lines, the angle is beta. And this is actually the line corresponding to the X direction, and this is for the Y direction. And these two lines are going to create two angles, theta 1. And these I will explain how these angles are coming, right? So the only given data for us is we know this angle, beta, this is something that we are getting. And we can get these two angles, right? This is actually the head of the robot. So if say this is actually the turning angle of the robot, right? Theta 1 and theta 2. These are actually input angles. These actually we get from varying the RPMs of the robot's wheels, right? So basically, if the robot wants to turn to the left, you increase the speed of this, and this robot will turn to the left. And at the same time, if you want to turn to the right, you increase the speed of this compared to this, and the robot will turn to the right. So based on that, there's this angle. So we call this the heading of the robot. So we know this, right? So basically, if you get the entire diagram, you know the MCR, you know the robot.
Excuse me, sir.
Yeah.
So we can't say that the theta angles.
Theta angles, I see. This one I'm talking about.
So we can't see that.
The ones you are drawing.
Wait, I'll stop sharing and share the screen again. Now can you see?
Oh, yes, yeah.
Yeah, okay. So this theta angles. And so basically, yeah. Now, this is actually, so the theta angle that I'm talking about. So the robot is moving here. These angles we can get. So you can derive a relationship between this heading direction. So heading direction and this angle, right? So this is theta. This is simply 180 minus theta 1, this particular angle. So based on that, you can derive something, but we will just consider this angle, the same thing, right? So so these we know. So if you get the diagram, of the of this this thing, you know the MCR, you know this angle beta. This is sorry about the confusion of these lines and all. Yeah, they are going right. So this is going through this, right? You get the idea, right? So beta, and this is x2 y2. This is actually the position of the robot at that particular point. We're considering a point position, and here we have x1 y1. Right? This is actually the center of, you can just consider this, that's the center of mass, right? For the robot at that point. Or the center of the anything, right? We are just considering one point of the robot, one unique point in both the cases. This angle is actually, if you draw two lines, that's the angle. So this is all that you get, and also the angle. angle that the robot is creating with center is creating with its line, straight line, right? So this angle, this is all we get. Now, how do we derive this? And also this distances we know, right? This is actually, so if you consider the moment to center of rotation, the distance from, so if you draw like a line through that moment to center of rotation parallel to the robot's like center axis, you can get the distance between the robot's left wheel and this line, right? So that is actually, if you draw a circle, of the robot's left wheel trajectory, it's going to be something like this, right? Something like this. And if you draw a circle for the robot's center axis trajectory, it's going to be something like this. And if you draw a circle for the robot's right wheel trajectory, it's going to be something like this. So the radiuses are given by these. This is the radius of the circle of the left wheel trajectory is RL. The radius of the robot's center axis trajectory is R, and the radius of the robot's right wheel trajectory is RR, right? So I think you all get the idea. If you all don't get it, let me know. These things we know, right? So as I will explain once again in Sinhalese for your reference. So robot කෙනෙක් ඉන්නවා. එයා දැන් වමට turn එකක් ගන්නවා මෙහෙම. ගනිද්දි අපි center axis අපි මොනවා හරි points එකක් ගන්නවා x1 y1 x2 y2 කියලා. x2 y2 x1 y1 කියලා ගත්තා. ඒ දෙක අපි යා කරනවා මේ කියන්නේ ඒකට perpendicular line එකක් ගහුවා මෙහෙම center axis එකට. ඒක යා වෙන තැන අපි වෙන horizon එක කියලා කියන්නේ ක්ෂිතිජය කියලා කියන සාමාන්‍යයෙන් සාමාන්‍ය අපි ගත්තොත් එහෙම මේ horizon එක කියලා කියන්නේ අපි මුහුදු වලට ගියාම මේ දැකලා තියෙනවා නේ කියන්නේ අර මේ මුහුදයි අහසයි නම් යා වෙනවා වගේ පේනවා අපිට. හරි හැබැයි එහෙනම් මුහුදයි අහසයි දෙකම parallel lines දෙකක්. යා වෙන්න බෑනේ එහෙම. ඒකට අපි යා වෙන lines දෙකක් අපි ගන්නවා එක මේ ඒ කියන්නේ virtual horizon එක නැත්නම් අපි කියනවා මේ vanishing point එක. ඒ කියන්නේ lines දෙකක් parallel lines එකක් යා වෙන තැන. මෙතන parallel නෑ lines දෙක. හැබැයි මේ අපි මේ moment එක ඇතුළේදී අපි හිතනවා මේ දෙක යා වෙනවා මෙතන කියලා. එතන මේ momentary center of rotation කියලා තියෙනවා. එතකොට ඒ lines දෙක අතර angle එක තමයි beta කියලා කියන්නේ. මේ time interval එක. t plus t dt කියන time interval එකේ හදන angle එක. ඊට පස්සේ එතකොට මේ data එක අපි දන්නවා. අපි දන්නවනේ මේ t1 කියලා කියන්නේ ඇත්තම robot ගේ control inputs වලින්. robot ගේ wheels වල control inputs වලින් හදාගන්න angle එකක්. ඒකට t1 t2 කියන එක වේරි කරන්න පුළුවන් robot ගේ wheels වල PWM values වෙනස් කරලා RPM වෙනස් කරලා turn කරන එක. හරි. අපි ඔය දන්න. ඊට අමතරව අපි RL RR කියලා කියන්නේ දැන් ඔයාලට පේනවනේ මේ curve එක මේ turn එක ගනිද්දි මෙතන මෙයා හදනවා පොඩි චාපයක්. හරි. පොඩි arc එකක්. ඒක අපිට පුළුවන් map කරන මේ circle එකක් විතර. ඒ circle එක නැත්තම් මේ චාපේ radius එක තමයි මෙතන RL කියන්නේ මේ left wheel එකට. ඒක සම්පූර්ණ robot ගේ center of gravity එක හදන එක R. right wheel එක RR. Right? I hope that is clear. So this is actually what the robot builds. So this is what we get. Now we have to derive this equation. So what we do is, I think it's better if I do it here. No, without going and making a mess over there. I think it's much more easier to do it here. It's not clearing it. Your drawings option is not working for some reason, so I have to erase. It's getting erased also. Anyway, we'll stop share and share again. Give me a second. Did I annotate in the slides itself? I think I have annotated in the slide. So anyway, it's fine. So I will just leave it. I will just do it here, right? Anyway, so we have these data. Now what? First, so basically, what do we want first to derive an equation? So we have to get these angles, right? You have to get these angles. So this, of course, you can see this angle. You can see, right? This is actually this angle is equal to this, right? This ekantara kon, right? If there's an angle like this, if there's two lines parallel, this is actually equal to this, right? This is x. You know this from, I think, A-level or O-level, I think, O-level mathematics. So this angle you can obtain as theta1, right? What about this angle? Same, right? This angle, it's also theta2, right? Same scenario, same Ekantara thing, right? So what else can we get? Now, basically, this angle we have to find, right? This angle we don't know. We know beta, but we don't know this angle. But if I construct a triangle, so I will just go to the whiteboard for this construction parts, right? So can you see the whiteboard now?
Yes.
Yeah. So there's x1, y1 here. There's the MCR here. And we know this angle is beta, right? You can just refer to the, I'm just explain some geometry here, right? Don't worry about this. So I know this, this is there. This is y. This is x. And I know this angle is theta1. Because if you consider this heading of the robot, it's theta1. It's parallel to this, so we got theta1. Now I want to find this angle. There's a small angle here. This angle. If I construct a triangle here like this, by your line here, so I know this is 90. This is 90. And so basically I'm drawing, if you like, look at this, if I go back to the screen over here. So you see, this is actually, I'm drawing a line from the center to here, right? So this is also 90 degrees. This is 90 degrees. This is 90 degrees, right? So this is 90 degrees. So this angle becomes 90 minus theta. 90 minus. This angle becomes 90 minus theta1, right? So once again, I go to the whiteboard. So this is 90 degrees, right? This is 90 degrees. And so this becomes theta1 from Ekantara Kona. This becomes 90 minus theta1. And if this is 90 minus theta1, this is 90, the sum of all the angles inside the triangle is 180. So this becomes theta1. Get how we got theta1, right? So we construct a triangle. This is 90 minus theta1. This is 90. So we get the sum of all the angles has to be 180 for a triangle, and this becomes theta1. And at the same time, now we have to find this angle. This is actually this we have to find. This we know it's beta. How do we find this? Now, once again, we can go to the this thing. This is basic geometry, okay? Not very complicated stuff. You go here. Once again, we can maybe construct a small a triangle like this, no? So we can construct a small triangle from here. This point. That's not how I wanted it to be, but that's how it is. So this is 90 degrees. This is 90 degrees. So this entire this is 90 degrees, right? This is 90 degrees. So this angle here, right? This angle is 90, sorry, it's theta2, right? Because this is theta2. This is theta2. This is 90 minus, this is 90 minus theta2. So this angle is 90 degrees. This angle is 90 degrees. This angle is 90 degrees. This is 90 minus theta2. Then this is theta2. This entire point is theta2. This is 90. Then this is going to be 90 minus theta 2, right? So that's this. Now this becomes Ekantharogan and this becomes 90 minus theta 2. So I think that you all get the idea. So simply you can just get, you can simply get this as theta 2 and this particular small point as 90 minus theta 2. Anyway, you get the idea. You want me to explain the angles, how you got the angles again? Can't I clear the annotations of this slide? Second one, yeah, someone's asking for the second one. So second one is this, right? So this is theta 2 and this angle is 90. Why? This is a perpendicular line, right? This is a perpendicular line. So this is 90. So this angle is 90 minus theta 2. So this becomes Ekantharogan because this becomes 90 minus theta 2. That's all that you can get it that way also. That is also possible. So I think that's easier, right? So second angle, you don't have to worry much after that because you don't have to get all the additions and all this. For the second angle, you can directly get this is 90 degrees. This is theta 2. This small angle over here is this one, right? Small angle is 90 minus theta 2. And this becomes equal to that. So we got all the angles now. And some prerequisites that you need to know from your O-level mathematics is that if there's an arc like this, like a curve like this, angle r, radius r, and this theta is given by r theta, right? And what else? So basically, this is all that you need to know, right? And all basic trigonometry is enough to derive everything. I go to the next slide. Now we have to, so SL you can get, right? SL is this one. SL is given by RL times this angle is beta. SR is RL actually, right? SRL is RR, simply RR times beta. But beta is not changing, right? The angle is not changing. Then finally, the entire curve created by the robot, it's equal to R times beta, right? So we got these angles, and beta is actually the change of heading. So simply you can see it's theta 2 minus theta 1, right? That's how you get beta. And you can basically equate these two together, this one and this one. So you get, if you like say, if you try to derive, 3 minus 2, right? 3 minus 2 is basically this one, that is basically the right, the curvature created by the right wheel, and deduct the curvature created by the left wheel, you will get this small curve, right? Whatever that's created by the entire robot. So you deduct those two, you will get RR minus RL times beta, right? So RR minus RL, you can see is this distance, right? The width of the robot, right? You can get the width of the robot like that into beta. And then you can basically isolate beta, that is by dividing this entire relationship by D. You get this, right? Just forget this part. Divide by this, you get beta, right? So then what you can do is you can simply get an expression for R, the radius, right? So this is equal to R beta. You can divide this entire thing by beta, and then you can get R, an expression for R. And then this actually, I think I'll have to explain a bit how you get this. So is this diagram clear enough, or do you think I have to go to the first one once? But if I go to the first one, no? So here. So how do we get the, so simply here what we're trying to do is, we are trying to get the final pose of the robot. Final pose of the robot, right? So that means this. Final pose of the robot as an expression. So how can I get the final pose of the robot as an expression? So if I go to the first diagram, right? If I go to the first diagram and I will here I can erase all this. So now I'm trying to find the current pose, right, of this robot. So how can I do it? So you can see, starting from the origin, we are here, right? We are here. So basically, whatever now first we will get the x direction. X direction first. Direction first, right? So if I want to get the x direction first, simply it's going to be x1 plus something, right? So x direction is simply this. So I'm trying to get this this direction, this distance, right? This is the final pose of the robot in next direction, right? Final pose of the robot is next direction. So this is this direction. This is what I'm trying to get. First up, this distance is anyway x1. No worries done. It's x1. Okay. Plus, now how can I find this direction? That's the next problem. Now I want to get this direction. This. Can someone suggest something? How can we get this next direction? The entire point of getting all these angles was for that, to derive this particular the expression, right? So we know we can get this direction now. These distances are all r, right? The radius, this from up to this point, right? Up to this point, this is r. This is also r. To this point. Now we know these distances, right? Now, if I want this much of distance, right? Basically, say from this MCR, from here to here, what's the distance? Can someone tell? This direction, this distance. Can someone tell this distance? What's the distance from here to here? Can someone tell? It's A-level maths. I don't know, O-level, I'm not sure. A-level. Can someone tell this distance? That is this also. I just want this distance. This distance.
R into cos theta 90 minus theta 2. Sorry, yes.
Yeah, R into cos 90 minus theta 2, that is fine. That is correct. And also, you can get with respect to this aspect, right? That is also correct. That is also correct. But also, we can get it as R into sine theta 1 plus beta. Or as the one answer, that is also correct. But I am going to get this expression in sine terms. I will explain why later. Basically, there's no reason, but yeah. But once we get the second expression, we can actually figure out why. So this actually doesn't matter even if you're getting cost terms, but by any chance, when you want, like say the moment center of rotation is in infinity, when the robot is driving, I will come to that later. Yeah, don't worry about that. So that is also correct. That answer is correct. So if you are asked to get this direction, it's fine. It's also correct. Now you can see, now we have this direction, but we want this, we just want this direction, this distance, right? This is what we want. Now we have this. So basically, if we deduct this part from this, we get this, right? So this part, how can we get? We have to deduct this part. We can deduct this part from this entire distance that we got. We get the small part that we want, because that's what we want to add, right? This distance into this. That's the pose of the robot with respect to the x direction. This distance is actually what? So there's θ1 here, right? I'll explain because we are running out of time. It's θ1 here, and these are sin θ1, right? So simply you derive r sin θ1, or if not, if we want to go with the cos terms as earlier, what he said, but I think I'm not sure who answered. If I want to go with the cos terms, then it is r cos 90 minus θ2. That actually becomes 90 minus becomes simply, I think, cos θ2, and then minus r sin θ1, or if not, simply r cos beta plus 90 minus θ2, right? Both are the same. Both are the same expressions, but you can get anything you want. Now, if you want to get in y terms, now the x terms are okay. Now say I want to get the y terms. So y terms are simply this, right? So we want to find this distance from here to here. This is the final pose, right, of the robot. Final pose of the robot. So y terms, this of course we know up to this point. This is y1. No problem there. Plus, we have to get this distance, right? Now to get this distance, simply we can just find this distance first, like the same way that we did earlier. Now this is easily sin θ2, right? These are sin θ2. But since we got the earlier terms in sin, we will get these in cos terms. Because if you, by any chance, if you want to get the angles, right? If you want to get the angles between x1 and y1, or the gradient of this, then of course we just have to divide y direction from x direction. And when we have the directions in cos and sin terms, we will get the heading, basically the gradient of the robot in tan, right? Because y over x, if it's if y is in cos terms, y is simply in sin terms and x is in cos terms, we can get it in tan, right? Or other way around, it could be cot. Anyway, if you want, we can get it. So anyway, the idea is to have them in different signs, right? So that we can get an angle. So we can get this direction, θ2. So if I'm going to get this in, say, cos terms, what can I do? So this particular distance, right? This particular distance up to this point, this particular distance, this one, I will take this distance, I will get another color, this distance, and this has to move a little bit further, is what? This, if you can simply get the y direction component of this line, you get this, right? This is what? This is r cos θ1, right? R cos θ1. R cos θ1, and we have to deduct this small distance over here, right? Then we get this one, actually what we want. Get the idea, right? Deduct the small distance. What's the small distance? We have this angle, that is theta 1 plus beta, if we get the, the y direction component of this r, right? This r, you get the y direction component, it's going to be this, right? This line has to move a bit down, probably might be confusing. The situation that we want. So this angle, this, if you get this one, that's what we want, right? So this is simply r, this minus r cos theta 1 plus beta. So simply the y direction one is going to be y1 plus r cos theta 1 minus r cos theta 1 plus beta. And the heading change basically is beta is equal to theta 2 minus theta 1. So I can go to the slide over there, and basically I can stack this up in the state space model. I can stack this entire thing, the state space model, like this. So x2, y2, and theta 2 is equal to x1, y1, theta 1 plus r, this expression, right? R sin theta 1 plus beta 1. This one comes here. This one comes here. And theta 1 plus, so what's the heading direction? Heading increment. Theta 1 is this. You get theta 2 by adding beta, right? Theta 1 plus beta gives you theta 2, right? So that's going to be beta. So I will show the finalized version now here. It's going to be something like this, right? Get it, right? Anything unclear? How we got this? Some basic mathematics that we did for O levels and A levels, but nothing else. Just that you have to think a little bit. And even if you all skip this cos and sine, you can basically flip these two, right? No worries. You basically can write this expression in cos terms. This can be written in cos terms, and this in sine terms. No problem. But make sure that this particular statement is in the same trigonometric format. This has to be, if you take this as sine, this entire expression has to be in sine. There's no rules as such, but it's much more easier for us to compute, right? When you get those in same terms, it's for further computation, it's going to be much more easier. So, but it's not wrong, right? It's not wrong for you to get the expressions in mixed terms, but it's recommended to get them in single terms so that it's easier for us to, do any manipulations, any mathematical manipulations when you have to do it further. And also, it's like because the entire state space model, the idea is to have it in the idea of the state space model was to derive the entire system in a bit more elegant form, right? So it's easier for us when these are in one single type of terms. Any questions up to this point? So this is how we derive the state space, the kinematic model. But by any chance, if the robot is say moving on a straight line, right? Then this moment to center of rotation disappears, right? As in, like, it goes to infinity. Then this r becomes infinity, right? Because if at one point the robot is turning like this, here there is a radius, but suddenly say the robot corrects its path and comes here parallel to this. Now this moment to center of rotation is in infinity. Then the r comes to infinity, goes to infinity, right? In that case, you can find, you just have to go there and substitute and see what the expression means. So you just have to say when the robot is going on a straight line, there's no angle of curvature. That becomes 0. the heading is the theta 1 minus theta 2 is 0, right? Beta goes to 0 and r goes to infinity. And then you just have to substitute and get this form, right? And say you're asked to explain this using control signals, right? UT, say like this. You're asked to explain this using control signal UT. Then, of course, there's two types of control signals. One is the linear velocity, and then we have the angular velocity of the wheels, right? Sorry, the robot's turning. The robot's axis turning, right? Turning around this axis is a yaw type of, there's three types of, motion, right? When it comes to rotations, how can I explain? There's a plane like this. I take a plane. So if the plane is moving around this axis, this is what we call roll. And if the plane is, sorry, this is pitch actually, sorry. Step. It's pitching, right? This is this direction, right? So the plane, it's a side view. This pitching. It's actually, if it's rotating around this axis, roll. And if it's rotating on this side, it is yaw, right? In a planar type location, the robot is moving around this axis. Actually, a yaw type motion, right? That's a 3 degrees of rotation, of freedom for rotation of a plane object. Sorry, any object, but only a 2D plane object can only have this type of rotation, right? So this actually we can get the angular velocity. It's beta, simply it's d over dt of beta, right? We can express this as this divided by time. So we can assume that there's the change itself is beta, and we can divide it by time, and it's beta. That's the rate of change of angular rate of change of angle, that is angular velocity, and the rate of change of the linear direction is s divided by dt, that's v. So we can simply substitute this into r, right? And simply substitute this into v over omega. So basically, you can. So we know that we got earlier an expression for this. So we can simply, equate dt, and we can get an expression for this. So, and we can get v over omega. We can just substitute this in all the r terms we got earlier, right? So we get the entire state space model as a function of the control input. Right? You just have to substitute this. Now I will go to state feedback control. Any questions from the modeling part? I'll go to the state feedback control and quickly cover that. And shells. This is a very short lecture, very short part. And don't worry, state feedback control will not be coming to the exam, but I did a little bit last time, but yeah. So state, so basically we discussed how if there's a robot, how we get the equations and get the model is actually for a straight line. And now, if I just basically cover the state space model very briefly, something that you all are very familiar with. This state space model we get. So what we get here is what we call the system model, system dynamics model, right? So we can basically the state space model like a recap. So if you have differential equation, second order differential equation, you can get these as a state variables. You get yt, the least order differential as our first state variable, second state variable, and the highest order derivative. We are not going to get another state variable, but we're going to write it as a different derivative of one of our state variable, right? So it's x2 dot, right? The derivative of this is this state variable. And now we try to find relationships between these, right? Between these. So you can see x2 dot is equal to x1 dot t, right? This is actually x1 dot t. Simply you get the differentiation of this, you get this. And x2 dot is simply this. So we get 3 state equations from that. And this is actually what we call exogenous input, the control input. This is an extra. If you see ut, that's actually ut is simply control, right? So this is actually like the force, or maybe like the motor input that we give, the PWM, right? It's exogenous. I mean, give an external current for the motor to rotate. Exogenous input. These are homogeneous inputs, right? And these are all system models. So we get the state equations like that. This actually is equal to x1 dot t is equal to x2t, and x2t is equal to a1. So sorry, we have to take this to the other side, right? These parts we take the other side, then becomes minus a1 x2t, and this is basically going to be minus a naught, and this is going to be plus b naught t. This actually has to be minus a naught x1t, right? This is wrong. It's minus 2, right? A small mistake there. I will correct that in uploading. Okay. Right now, going to be a naught x1, right? X. I'm going to forget this, and it's going to be wrong, right? So basically, if you write this in matrix form, you get this, right? It's a differential state space model. So simply you stack them up. So this x1 state equation is this. It's this one. So there's only x2. So one coefficient there. No control input, 0. x2 dot minus a naught into x1 here. It's minus a naught x1. It's here. Minus a1 x2 is here. And now here there's a control input. So this is this. So if you all remember from this controllability observability, this variable, this state variable, or basically this state variable x2 is controllable. See, you can control it. It's a controllable variable, right? So I will come to controllability and observability. Have you done controllability observability for controls? Controllability observability have been covered.
Yes.
We have done it. So you all don't. So basically, you get the state space model, you get the system matrix here, you get the control matrix here, and this is the control matrix, system matrix, control matrix, and say that you want to observe one. Say I want to observe x1, then I get this. I get x1 out, right? If you want to observe both x1 and x2 variables, I put 1, 1 here. If I want to observe x2, I put 0, 1 here, right? So simply you can conventionally explain it like this. This is a system matrix, and that's the input drive matrix, or the exogenous part, or we call it the control matrix. We had the output matrix here, and D is actually the feed forward the direct transmission matrix. You don't have to worry about that. That's always 0. Think of it like that. So controllability. So for state feedback control, so you all know for control systems, you all have done SISO type of control, single input, single output type of control, right? So in this case, we actually considering multiple input, multiple output type control. So it's like MIM. So we have multiple states, and for all these states, we have to control by having multiple gains, right? In actually in a single input, single output control, we had a single output. We had the transfer function, and we got the output of an input relationship. That was the only input that we had, and we gave our based on, sorry, that's the only output that from the system that we're observing. We get that into our controller, and maybe we give maybe some control values. Okay, proportional gain, a derivative gain, integral gain. These are all in one block, right? One block, and we control. So it was something like this, no? You had the plant, here, say GS. You get the response, say YS. And say we had the control signal US here, and this US is actually dependent on RS. Yeah, this HSO here. This was what you got, right? Simply we can, there's another block for this, but you can write it as this, right? So this actually, we have the controller here, CS. The CS can be anything. CS can be PID, PD, or simply P. You can have anything. Based on that, you can generate the US. Here we have the ES error signal, and the control signal is here. This is what we had now. This is single input, single output system. The control is basically single input, single output, right? This, if you take the CS block, you have a single input, that's the error, and you have a single output. But in our state feedback control, we have multiple inputs, right? X1, X2, X3 can go up to multiple states. And to all these states, we have to give controls. Right? That's why we come to the state feedback control. So now, basically, for the state feedback control to happen, first thing is the state has to be controllable. Right? If the system is not controllable, then of course we can't control anything. The system has to be controllable first. So controllability can be so basically explained as so if there's two states of the system, X0, X2, XT, in a given time, right? In a given time, we should be able to manually control the state transition. So say, imagine you place a ball on like a angular, like say a wall, right? You can't control the ball's acceleration. It's going to accelerate. So you just place the ball over there, it will fall down, right? If you like to just think of this, you just drop a ball from like a window, right? You can't control the dynamics of this ball. It's going to be dependent on the gravitational acceleration. You can't control that. But say you are throwing the ball at someone, right? Then of course you can control the input that you're going to give, the angle that you're going to give. You can control all this. So basically, in a given time period, the transition of this, if you can control it, that's controllable. So if you get a system dynamic equation, X1 is equal to say X2 plus say Y dash ut. Now this is a control. This state variable is controllable, right? Because we can, by changing ut, you can control that, right? But if the ut was not there, it's not controllable. It's all homogeneous, right? Whatever system parameter is going to decide how this is going to be after a certain time. It's not controllable. So the system has to be controllable for us to implement the state feedback control. If any state variable is not controllable, then we can't do this. Then we have to go with some other method like adaptive control or basically gain scheduling, something like that. State feedback control cannot be done, right? Yeah. So how do we check if the system is controllable? It's by getting this controllability matrix, right? So simply you got the C matrix, you stack them up, B, A, B up to A n minus B, and if the matrix is full rank, then you have full state controllability. Full rank as in the rows of the matrix are linearly are not linearly independent. say like you think you all have done this Gaussian elimination, right? Gauss-Jordan elimination for mathematics. So you have like a row of a matrix, say something like this. An example. So there's a matrix like this, say 1, 1, 0, and this is linearly dependent. You can multiply this by 2, first matrix by 2. So R1, 2R1 into R2. This is linearly dependent row, right? So you can't have this type of this is not a full rank matrix. For a matrix to be full rank, the rows have to be linearly independent, right? So if you have 1, 2, 3, 4, 5, 6, now this is linearly independent, right? You can't maybe add something or multiply something and get this row. That's what we call full state control. And then we have observability. The system has to be observable, because if you can't observe the control system properly, you can't design a state feedback control. Observability is there. So that is actually checked by this matrix. So you have the observable functions into A, you get it. I do a small example, then you understand, right? So this is like how we actually like get this. There's something called a feedback law we explain. Just for the time being, don't think much about that. If you have like a system, you have this minus kx type feedback law implemented. This is the control signal. So k is actually what we call the state feedback gain. X is the states. X can be like a vector, like X can be multiple inputs, right? So n-dimensional vector, right? So that's about that. So this is actually like the broken down version of this. You don't worry that basically X dot. If you want to implement this in Simulink, you want this model, right? X dot is like the rate of change of the state variable, and X is actually the integration of that. Get the integration, and you get AX plus minus KX B. So basically minus K BX, right? This equation. So we get this equation, right? U is equal to minus KX, right? So you get AX plus AX minus B KX, right? AX plus minus BKX. And that's actually the state feedback control. This equation is obtained, right? So, and we get out of this state variables, we want to observe something, we get it from the C, right? Okay, now I will, so, okay. And also, I'm not sure whether you all recall these things. I'll just briefly go through. For a system, for us to decide on the system stability, we do something called the pole placement, right? That's what we do in the root locus. We actually place the poles in such a way that the system is stable, right? Don't worry much about this. So I will not go to in-depth because we are not covering controls here. I just want to show you how to get the state feedback control into the mobile robot, right? So basically, pole placement is basically done by, so if say the system is stable for certain pole placement, right? So you all know that there's a system like this, imaginary and real. So if the poles are here, the system is unstable. The poles are here, the system is stable. Here it's marginally stable, right? So you want our poles to be here. Sometimes complete stability probably might not be exactly what we want. So we probably might place two, this imaginary poles, and maybe one over here in the real axis. So negative part of the real axis, and we eliminate these parts. So pole placement is something that we want to do. So basically what we do is in traditional controls, we have a body plot or root locus. So we find out where the pole placement needs to be done to obtain the system stability, and we place the poles. So in this case also, so the system characteristic equation. So for a traditional system, you got this characteristic equation, GS over 1 plus GSHS, remember? Similarly, the traditional equation for state feedback controller or any state space model is this, right? This is the gain. So entire objective of control is, so in this case, we have the CS, right? So by changing the CS parameters, we control the system dynamics. In this case, by changing this K value, we actually control the system by changing this K. So that's the entire idea, right? So this is the example, right? So we have a system matrix like this. Let's say from a mobile robot, we have a system like this. This is the control. So basically, we are having one control input. Say that is for X3. This is third order model. We have a control, input for the third state variable, say X3, and we are observing X1, say the position, right? So we have a state model here, say the mobile robot model. So now they're asking us to design a full state feedback controller for the below system and place the closed loop poles at this particular point. This is conjugate. The conjugate as in like imaginary conjugates, right? What do you call that in signal is conjugates as in like can't remember. Basically, if you have imaginary axis like this, there's one here, 0 plus 4i. This is 0 minus 4i. These are complex conjugates, right? Complex conjugates. Now they want us to place the poles in this manner. So minus 2 minus 2 plus I4, that is somewhere around here. Minus 2 plus I4 minus 2 minus I4 and minus 10. So they are saying, okay, for this particular parameters, the robot is stable. So the robot is a line following robot, right? So when these particular variables are given, the robot quickly fits the line, right? Something like that. Now currently it probably might be going like this or something like that when it's following the line. So currently it's like this. Currently the robot, when following the line, come across an error, it actually goes to this territory to stabilize. But with this particular gain values, it can stabilize like this. That's like the idea, right? So for these inputs, the robot is going to act like that. So how do we do this? That's the question. So first up, we have the system like this. We just substitute everything into this form, right? Nothing else. Very simple. So there's the, S is actually, SI means you simply multiply an identity matrix. There is one identity matrix, is like, if I remember from maths, if you have a 3 by 3 matrix, diagonal is 1, right? Diagonal is 1. You multiply that by a constant S. Constant S is simply j omega, like what we have for the Laplace constant, right? We multiply by S. So S, we multiply, and you get this matrix. Minus A is the state matrix, and B is this. K is the Kalman gain, the state feedback gain. K1, K2, K3, right? You then what you do is you multiply these 0 into K1, 0. As this is a 3. This is actually a 3 by 1 matrix. It's a 1 by 3 matrix. So what should you get? 3 by 1 into 1 by 3. So simply get 3 by 3 type matrix, right? So, but anyway, it doesn't matter because this becomes cancelled, right? 0 K1, and simply after multiply all these things and you do the addition and all this, you have to get the equation like this, right? So this is actually what we call the characteristic equation. So you just multiply and see, or you can use MATLAB to multiply, anything's fine. So once again, after doing all the multiplications, you get this type of equation, right? Now they are asking us to place the poles in this. Any questions up to this point? Have you any issues? How we obtain this or anything? Simply you multiply this here, and you get 3 equations like this equal to 0, and then this particular sign means the determinant. So basically, the characteristic equation is the eigenvalues of the matrix, right? Eigenvalues you get by getting the determinant of the matrix in this case. So you get this particular matrix done. This is that particular matrix, and these lines mean the determinant of the matrix, and you get that. You get this, right? Determinant, of course, of a 3 by 3 matrix, because you are getting 3 by 3, because this is 3 by 3, this is 3 by 3, and this is 3 into 1 into 1 into 3, that's 3 by 3. The addition of all 3 by 3 matrices will give you a 3 by 3 matrix. The determinant of a 3 by 3 matrix, you know how to get it, right? You get this one, this S into whatever. I mean, what's there? I mean, I haven't done the solving, but once you get the determinant, you get a third order 3 by 3 matrix. That means third order system equation like this, right? You get this equation, and it's a matter of finding. So it's a matter of finding the poles, right? So fine. Yeah. So now pole placement is what you do. Now, okay. Now we got this equation. This is a system equation. Now they're asking us to place the poles at these locations, right? Now what do? We derive the system equations for these locations. How do we do that? So they say, okay, these are the poles. So we got 3 system equations. For this is for the pole to be at -10. What should be the system equation? S plus 10 equals to 0. To get this pole, S plus 2 plus I4 is 1, or J4, whatever. The other one, S minus 2 minus, sorry, I got it wrong. It's plus here also. This is the one that is changing. Minus J4 is equal to 0. So you got these 3 equations. You multiply all these together, and you will once again get a third order system equation, right? Get it right? S plus 10 into S plus 2 plus J4 into S plus 2 minus J4. You multiply all these 3, and you'll get a third order system equation. Now you have two. Now you have this is actually this equation is a desired system equation, right? You have this. You have the current system equation, currently what you have, and you have the desired system equation, right? You have the current system equation, which was what we got here, and we have the desired system equation. So how do you make the current system equation, current system into the desired system? You basically give these values, right? You obtain these values, but the desired values that you got here, you give it to this, right? You give it to this. How do you give it? Just do a coefficient. You just compare the coefficients. So you say S squared, S cube is anyway 1 over both. For S squared, it's 14. So to make it 14, you have to equate this to 6 plus K3. So 6 plus K3 is equal to 14. What is K3? K3 equals 14 minus 6, that is 8. Right? K3 is 8. Right? Similarly, you can do the system coefficient comparison and find out K1, K2, K3 values. So basically, it means there are 3 state variables, x1, x2, x3. If we give these 3 Ks, K1, K2, K3, if you give these 3 Ks to the system, these 3 values, similar to PVPRA tuning, right? Then the system will obtain that this is the unstable trajectory of the robot, stable trajectory. You give these 3 values, the system becomes stable. Okay? It's it's very simple. It's not very complicated, right? So I have modeled this in MATLAB. And this is how we get it, right? I can show the MATLAB code, so it's actually so you all figure out how easy this actually is implementing, because what matters in the end is implementing, right? Regardless of what you do, implementing is what matters. So so I will just wait until I will do the remaining part until MATLAB loads, right? So any questions up to that point? State feedback control, you all are clear. So basically, I can show the rhetoric. So simply, this actually is the step response initially. This diagram doesn't actually do justice to our design. So you can see the amplitude here, the peak overshoot here is close to 1.1. But in this case, you can see, even though you can see the oscillations, the amplitude is very small. See, it's actually going at 0.03 level. So actually, it's very, if you consider this is millimeters, this is like 1.1. So we consider this as centimeters. 1 centimeter. This is like 1.1 centimeters. That's a very big oscillation. Here we actually, and it's actually going there like that for almost 10 seconds. See, settling time is around 14 seconds. But here is settling at around 4 seconds. It's actually a very zoomed out version. It's settling at around 4 seconds at 0.03. Small offset is there, right? Small offsets like 0.03 millimeters. Right? That's not actually very negligible. That much of settling time is obtained in 4 seconds, right? That's actually very impressive, to be honest, for the system to obtain that type of stability in that small time. This is by state feedback control, right? State feedback control can be done for manipulators as well. So you can go through these, get the rotation matrices, transition matrices, get the Jacobians, and then you got 3 state variables. Get the state space model, state feedback control design, right? So that we get the Jacobian. That's what we mainly do. The Jacobian vector. Same method. There's no huge difference. Same method, but we actually don't go for state feedback control for manipulators, but maybe for gain scheduling. That's where there are different types of controls, right? We have done PID, then we have observer-based control. Then we did state feedback control now. Then there's adaptive control, right? And then there's optimal control, and also there's a new type of control machine learning mix, which we call as reinforcement learning based control. Right? These are actually the control types that we have, and there's gain scheduling, right? So many types, and for the system that we are considering, we have to decide what type of control that we have to use, right? Any questions from state feedback? So I will go to the code. So can you see the screen? MATLAB.
Yes.
I think I can go to the state feedback controller. So simply, okay. So this is the state feedback part. So we have the system matrix here, B matrix here, and it's not optional. This is required. This is actually to obtain the output matrix. No disturbances, no feed forward matrix. And here I'm finding the state space model is obtained by this S command, right? MATLAB inbuilt command. You give the inputs in matrices, and you give the state space model, assign that to system variable. And then I can calculate the current poles here. So based on eigenvalues of this matrix, eigenvalues of this matrix is what we consider as the poles of the system, right? And these higher poles, of course, is these, right? And when you give this simple command like k equals place ABP, so A is actually the system matrix, B is actually the this control matrix, and P is what we want to place, the poles that we want to place. MATLAB will itself calculate and give us the everything that we did manually. MATLAB will calculate and give us the k values, right? MATLAB will calculate and give us the k values here. See. So, and it gives us the new poles as well. Now the new poles are the desired poles. See, these are the desired poles, and the new poles are those, right? And it will calculate, and within like 20 simple code lines, we have the entire system model, right? It's very simple, that's what I'm saying. So you can simply tune a system very easily. This is MATLAB itself, right? And I think I have obtained this figure. So here, figure 1 is for figure 1. I have obtained as for the system without, the new state space model, right? So if I run this, you can the new system. So this is the tune system, right? This is a different system, not the one we saw earlier. System. So that's also it's very impressive. See, it's very small amplitude, very small settling time. See, so you consider this a line following robot, right? This is the line that the robot has to. This is the reference line, right? So this is the reference line. So the line following robot comes very soon to the settling point with very small overshoot, right? So almost as this, you consider this as a line. This is the line, the reference line, and this is the overshoot of the robot, the trajectory of the robot. Small overshoot and a very quick settling time. See, so that's actually very impressive when it concerns when it comes to robot control, right? Because we want this. We all have worked with robots, and you all have seen that the robot how chaotic sometimes the movements are, right? It goes here and there, and when you're following the ball, it actually like keeps spinning, and all these things happen. But if by tweaking certain like 3 variables of the entire system, we can simply control the robot very, very effectively, right? Okay, so that's basically about state feedback control. It's a very, very interesting area actually, state feedback. And now I'll come to SLAM as a closing note and quickly go through that. It's very small. All these things, so SLAM and state feedback model, state space model, all these things are very new actually. These are very new technologies, new as in like close to 50 years old, like compared to what other stuff that we're learning, like all these other areas that we are learning. These are very new areas. They were actually developed in 1970s by state space modeling, state feedback control, the Kalman filter, estimated Kalman filter. All these things were developed by a scientist called physicist or a mathematician called Richard Kalman. Right, in 1970s, he was he wanted to develop this. There were so many inefficiencies in mobile robot control, and more than that, this is actually in the Cold War and all, satellites basically, or space systems. So in these areas, there was a huge demand or huge requirement for optimal control, right? So you send a rocket or a satellite, right? You are the engineer at say NASA, and you do the calculations, say there's a huge tolerance required that we can't work with huge tolerances and huge uncertainties when it comes to space, right? Say mobile robot, if it's not going through the line, you can at least pick that up, maybe do some tuning and then place it. What about a satellite or a rocket? You can't, you're not Superman to fly to the rocket and do any altering. You can't do that. So you have to be very precise, and your controls have to be in optimal condition when it comes to these space missions. So Kalman developed this state space model so that he can look at the system in a broad way. He can see all the state variables associated with it. And also he can control the state variables by himself, right? Or by ourselves. We can simply give that gains and we can control all the states as long as the system is controllable and observable, right? So now, there, of course, the application of Kalman is actually SLAM. SLAM, once again, is not entirely dependent on Kalman. There are different types of SLAM itself. So I will come to that. So I will just go through briefly about SLAM, once again, I think we covered these. SLAM is basically simultaneous localization and mapping. So it does the localization and mapping at the same time, right? It maps the environment, it localizes. So mapping is simply basically the estimation of the map with respect to the known pose of the robot. So you know the poses of the robot and you draw the map. It's like I took the example. You know where you are and you draw the map, right? So you know street, you know all the locations. You come inside, you know the gate, you know the cafeterias, you know the bird's nest, the open areas, ground, engineering faculty, business faculty, all these things you know. So you know the areas, you just draw a map, right? You have the mental location in your head. Okay, this is where I am, right? And say, or basically, if you are given, like, say you have to survey the entire area, right? You have to survey the entire area. Say you have to mark the distance from the engineering faculty to the birds. You can do that, right? There's no problem there. You know the entire area. So you don't have to localize. You don't have to say, okay, where I am now? Where's the engineering faculty? Where is the new building? Where is the ground? Where is the swimming pool? You don't, swimming pool, of course, you probably might not know, but other areas you all know, right? So you have the map in your head. Sorry, the location you know, just have to measure and put. And what about localization? It's like you know the map, and with respect to the map, you have to find your pose. It's like what you do in Google Maps. You have a map, and you look at the map and figure out, okay, I'm here now. And you move for more like 1 kilometer, 2 kilometers, and you find out, okay, I have moved 2 kilometers to this direction, to the north or south, and this is my current position. I'm near, say, the Malabar Junction, or maybe near the Cardwell Junction. So you can figure out, right? So that's basically localization. But if you don't have both these, you don't have the map and you don't know the position, right? Then you have to do this simultaneously, and you have to do the localization and mapping at the same time. That's the SLAM problem, right? So the SLAM problem, you can read this, right? Unknown environment. So you can read this. I'm not going to go through all this. I have done this. So it's a chicken and egg problem, right? So it's like, the chicken and egg problem, which came first, chicken or the egg? Something like that. You have to localize. To localize, you need the pose. To map, you need the localization, right? So this actually has to happen simultaneously. So this is how it's done. And we have certain, so this is actually, I will show some videos to get an idea. I'm not sure where it was. I got there are 4 videos actually I want to show, but we'll see with the time. So this is actually like, so yeah, I will explain this. It's a project done by some university. So this actually is the robot. Can you all see the screen? Can you all see the YouTube video?
Yes, sir. Yeah.
So basically, this is the robot trajectory. So this is actually the green one. So if you all remember, I said earlier, there's this odometric mapping, right? Field odometry. Like based on the encoder positions, you can basically map the robot's trajectory, and also you can map based on the sensors. So this robot is actually the green path is actually based. This is actually estimated Kalman. They are doing this. They are doing the mapping, and at the same time, you can see the odometric trajectory in red, right? You can see the difference. So I will now at the moment it's all almost. We can see when this turn happens, the actual position is obtained by the estimated Kalman, but the odometric reading is showing something else. See, this red one is wrong. This is what actually given by the wheel encoders. So you can see this SLAM is odometric. Odometrical mapping is wrong, and SLAM is giving a very precise mapping. You can see by the end of the mapping how inaccurate the odometrical mapping is, right? this green color background that you can see is the map that they're building, right? They're constructing a map of the environment. Yeah. This is what we call full SLAM, right? They're not only looking at they are creating a map, they're storing a map, and not just features at an instantaneous time. You can see the difference, right? See between the odometry and SLAM map. It's actually you can see how alarming now this map is going through this wall, right? The odometric map is going through this wall. See, it's not accurate at all, right? So this is the final model, final map. See, the odometric trajectory is wrong. See, it's going through walls and all these things. But the SLAM trajectory is very accurate. See, and also I want to show this using this estimated Kalman. I wanted to cover Kalman for you all, but I couldn't do that. Maybe I'll add a video or something after this. So this actually now they are tracking the movements of this cherry using basically vision, right? So vision tracking is done, shown in the green rectangle, and this red rectangle is actually what's the estimated tracking, the estimation or the probabilistic tracking done by the Kalman, right? So you can see that by the visual input, the sensor is gone. Now the camera can't track this. The camera can't track the movement of of this object, but the Kalman is estimating that. Even when the input or the sensor input is lost here, right? Sensor input is basically lost. We can figure out how the object is moving, but a computer can't. But the Kalman filter seem to tracking that. See how accurate that is. Even though it actually moves, the sensor input is completely lost. The estimation can actually track that. See, so that is actually how powerful this Kalman filter is, right? So, and also this is actually something that I showed about the covariance, right? There are covariance, the uncertainty of the robot growing. You can see the locations, actually the uncertainty of these particular landmarks are growing now. And as soon as it comes to a landmark that it has visited, all the uncertainties are sort of like reduced. We can see at this point, now we can see when it starts at this particular point, this is like the 0-0 position, right? Now there's no uncertainty. The robot knows, okay, I'm starting at the 0-0 position. Now once it starts moving, now it finds landmarks like this, keeps mapping, and now you can see the uncertainty of these landmarks are also slightly increasing. And you all remember that I took an example of I think Ravinath navigating through unknown terrains. So now it's like he's moving towards certain areas, unknown terrains, right? Now he's like, okay, was it exactly here? Was this landmark exactly at this point? Now he's slightly becoming unsure. And at this point now he's becoming very, unsure about where he is, right? So now it starts growing. The uncertainty is given by this Gaussian, I told you, uncertainty, even though it's shown by this circle, it's actually a Gaussian curve, and we are getting the top view. So basically we are assuming that the Gaussian, like in the Gaussian, I can draw here. So Gaussian curve is something like this, like that. So here the center is actually the mean, right? U bar. So this is actually what he sees as the actual estimate. But you can see there's an offset. See, he's thinking he's looking at this miles to all the landmark here, but there's an offset here. Of course, the offset is very high. See, he's thinking it's here, but it's here. So this is actually probabilistic state estimation. Now, as soon as it starts moving, you can see that the uncertainties keep growing. See, it's very high now. Now it's very high. The uncertainties are almost very high. But now, once he comes to the starting point, this was the starting point, I think it was the starting landmark. Okay? These green bars are now known points, known landmarks, earlier mapped landmarks. And it comes to that, you can see everything actually suddenly, all the uncertainties suddenly disappear. Right? Once it comes to this point, you can see it sees another landmark that it is already seen. So he has gone full circle and come to the point he started. Now he's a bit sure now about all the landmarks. Now he has an idea. See, now at this point, everything reduced, right? Not zero, but the uncertainty is reduced. So this is actually what we call loop closure, right? Loop closure using estimated Kalman filter or estimated Kalman filter slam. You know what estimated Kalman? Okay, so I will go back to the slides and quickly finish that off. So there are different types of slam. These videos actually relate to those videos that I showed. I'll share the slides. You can actually go and visit these and watch. Okay. So why slam is important? It's obvious, right? Mainly for these areas, space exploration, underwater mapping, all these things, right? So basically, defining the SLAM problem is that you have been given the robot controls and the observations. Controls, you know, the motor controls or the wheel commands. Observations are what you get from the sensors, right? And you want from these to develop a map and also the trajectory of the robot, right? So trajectory of the robot is simply the localization. What we did, x1, y1, theta 1, that's the trajectory. The map is basically the locations of the landmarks, the occupancy rate, all these things, right? So given these, how you get these as a problem? So there are different types of SLAM, online SLAM, full SLAM. So you can see that here in online SLAM, this is what we commonly do. So this is the previous state. This is actually in discrete time notation. T minus 1 is the previous state, T is the current state, and T plus 1 is the next state, right? So given the the control input and the sensor input, you get the map location. And after you go to the next point, all this data is discarded, and you simply use this state, and you can use this control input and the sensor input to find out the next state and derive the map location. So you are basically mapping in a momentary way, right? One data at a time. But full SLAM, the example that I showed earlier, is actually taking into account all the states, and it's locating all the states, it's localizing all the states, and giving a map. It's just usually infeasible in real time. It is actually feasible, but it needs actually high processing power for the computers. So basically, it's space exploration once again. I use space exploration very commonly because it's like one of the most, mobile robotics and SLAM is mostly used in these areas. There's Mars rovers and all these things. Because we can't control them also, we see the systems have to be very precise and very optimal, right? You can't actually change these things. Now in this case, what happens is actually the robot, the Mars rover or the robot actually does online SLAM. But what it does is it feeds all this data, xt minus 1, all this data is fed to the satellite. And the satellite, maybe in the space station or in Earth, they do the full SLAM based on these inputs, these state inputs, these control inputs, and these sensor inputs. It does all the mapping. So it constructs a map of Mars or whatever, moon or whatever, in the satellite or in the space station or in Earth, or the control station in Earth. The full SLAM is not done in the robot. Because the robot can't have, because there's a lot of processing power, is a multi-sensitive platform, so many sensors giving so many inputs, it can't allocate a lot of space in its computational and its computation capacity cannot be wasted for that. And so what it does is it actually does a local SLAM, online SLAM in the position, and gives the full SLAM model to the controlling area, right? So there's volumetric SLAM, feature-based SLAM. Volumetric SLAM is once again creating the entire map. Feature-based SLAM is looking at certain features, say color features or basic obstacles, right? Not the entire thing, right? You can read through these. Not important. I mean, important, but just get an idea about this, right? The static SLAM and dynamic SLAM. Static SLAM is like where you do the mapping and localization for a static environment. Dynamic SLAM is like the map is continuously getting updated, right? Static SLAM, what we do is this is a constant map, and after the map is done, say it's like a workplace, like a factory work area. When no people are there in the factory, you do the mapping. That's actually static SLAM. You have the map. Now you don't have to do mapping again, right? Once you have the map, you don't have to do mapping again. And by after that, when there's people going around or dynamic objects come into the picture, these are treated as outliers, right? These are just outliers. At that particular point, they take those into account and maybe more. That's it. Dynamic SLAM, of course, the map is also evolving, right? Map is evolving, and also the SLAM algorithm has to continuously run. The mapping has to be continuously done. Yeah, that's what dynamic SLAM is. And active SLAM, passive SLAM. Passive SLAM is basically there's an observer. The observer is actually building the entire mapping based on whatever the inputs you are getting from the basically you are there in a vehicle, right? So you are in Anuradhapura, and you want to basically build a map of Ruwanmalisaya and Jetanaram, right? So say you are in the passenger seat. The driver is driving. You can't tell the driver to go here and there. You, based on the driver's movements, you just draw. Okay, so there are the Ruwanmalisaya is here. The Kalayu is here. The Jetanaram is here. You just map like that. In active SLAM, it's like you can command the driver. You say the driver, okay, go near that. I want to get this particular location. I want to get the distance between Dudukamrajuro's statue and the direction of those two. And I want to get the distance between the Jayasri Mahabodhi and Ruwanmalisaya. You measure all this, right? You actually get an idea of all this going on. You actually have a commanding power to control how the the dynamics of the system is moving in order for your SLAM to happen. In passive SLAM, you don't have it. Whatever UT you get, whatever UT and whatever ZT you get, right? Sensor input and control input you get, you based on that, you do a state estimation. But in active SLAM, you have a control on UT. You can control UT in order to get the ZT. Understand? ZT and basically XT. You have a power over ZT. UT. You can control UT and get the inputs as you want, right? That's active SLAM. And then we have multi-robot SLAM and single SLAM. Single SLAM is for a single robot. Multi-robot SLAM is for multiple robots. I had a video here also for that. Should be here, right? Multi-robot. So here, basically, multiple robots are doing SLAM, right? So you can see the covariances or what the uncertainties between the landmarks and are basically reduced in a basically dependent way, right? If this robot has the map already done, this robot goes near there. The dependency, based on the dependency, the uncertainties or the covariances, error covariances reduce, right? That's the entire idea. So that's about that. You can watch the video after exam maybe. Uncertainty in SLAM, you can check that. That's it. No. And as I said earlier, there are three major paradigms of SLAM. There's extended Kalman, there's particle filtering, and graph optimization. All these three methods are used, but we are highly looking at the extended Kalman filter, right? So, yeah. Once again, no single best solution to SLAM problems, right? You can decide on that. Not only to SLAM problems, in any general localization mapping control, there's no single best solution. right? You have to decide on that. It's very open-ended. So one person can come up with something, the other person can come with something else, right? You can't say, okay, this is my idea, is the best idea. You can't generalize like that. When it comes to robotics, you can't say, okay, this is the best idea. It's a continuously improving and adapting field. So, and based on cases, you have to decide what's best, right? So that's what I want to say as the conclusion, that based on the case, your system has to change. This will be important for your exam as well, right? So, I'm not someone who gives straightforward questions. I think you all probably might know from what I have given for lab scenarios. So, and I don't extract questions from here and there, right? So I have to prepare my own stuff. So if you are given a question for a case, look into that case, right? Because I don't give any case for just fun, right? You can just go through that and get an understanding of the particular environment, and for that particular environment, what sort of this thing has to be done, right? So don't generally go with whatever you know. Okay, say okay, wheeled robotics is the best, or legged robotics is the best, or differential driving is the best. No, you can't say that, right? You have to look at the environment, and based on what we discuss, you have to understand. Say you want to say go with a micro mouse type robot, you can't. It's not going to be feasible for you to go with something like a holonomic type, or omni-wheel type robot, right? So you might have to go with something like differential drive. But say for something like you want to climb stairs and all, in that case, you will have to go with a robot that has tracks, right? You can't go use a differential drive robot to climb steps. So if you have an environment where you have to design a tourist guide robot, right? So as I said earlier, you have to design a tourist guide robot for say a beach, or say Yala. Yala, of course, it won't work. Say Anuradhapur once again. There's a lot of steps over there. There's sand type of environments. So you have to figure out what exactly matches those, right? You can't simply go with, okay, some robot, some wheeled robot, it will go. You can't do that, right? So you have to look at the scenario, you have to look at the environment, the terrain, and then decide how you have to design that. You can't generalize saying, okay, this robot that you make for Anuradhapura will work for, say, no radio. You can't say that. Different environments, different conditions, different type of robots, different type of algorithms, right? So that's actually case-based analysis. You have to look at the case, you have to analyze the case, and then understand what you are going to develop. You can't generally say, okay, I'm going to go with this. And also, that's basically about. And also just go through what we did last week. I did some of the areas as recap this today also. Go through them. Once again, the exam is not what matters, right? Exam is something you can always get through. It's a matter of implementing this in real life, right? How you can basically work on this in real life, and how to get this done. If you are given a problem, how do you approach that, right? Doing some mathematics in the exam is not what actually matters in the end. So you can do all these things. As I said, that entire state feedback control can be done in few lines in MATLAB, right? So this estimated Kalman filter also I wanted to do some coding. But I can do is I will share a notebook, a Python notebook on that based on my time availability. So I can just go through that and understand how the estimated Kalman filter is implemented for a system. Kalman filter, of course, the deriving part is very complicated, but I'm not going to go through that. If you want, I can do that. But I don't think it's necessary, because you can just use the inbuilt algorithm, give the system state, and get the predictions, right? Get the estimations. So any questions from your end? Any questions that you want to clarify or cover? Any issues? Or any questions regarding the entire module, or anything that you want me to like further do or anything? Okay, then I will take silence as I think it's okay. But if you all want any clarifications or anything, you can contact me. You can also like direct anything issues that you can't directly contact to me to directly convey to me or to Thilan, and he can talk, right? Yeah. And also the question, actually, the one that I am giving is actually it is basically one question, and it has 4 parts, small parts. It has some analytics, like basically some mathematics throughout by already derived, and a little bit of open-ended questions, right? Open-ended, like practical questions, like yeah, you have to answer based on the case. And also, don't waste a lot of time. I don't want very lengthy answers, right? As long as you can explain everything in short, that's enough. So if the idea is conveyed, because for that, of course, you have to have the idea, right? You have to have an idea. So just write the answer, and that's it. You don't have to waste my time on my question. You can directly go to Miguel's questions, right? I don't have to waste time on this one. You can use this as a time-saving option, right? But as long as you know what's done, right? Just right. Right? Any other questions? Any issues? Okay, so then based on the time availability, we will see if we can do a little bit of particle filter and estimate Kalman filter maybe after your exams. I maybe can, if I have time, I can record a video or something and post, because I think that's very important, right? Something that's not covered. In this case also, it was not supposed to be covered, but I just want to do that because just wasting a lot of time on kinematics is not going to be beneficial as long as, I mean, it's already there. The model is already there. Differential drive robot, the model is there. Kinematics models, they're already there, right? So you don't have to waste time on those. So that's right. So there's another small question, right? How would be the structure of the paper? I'm not actually sure, right? I didn't see the paper, but my question was supposed to be 25 mark questions. That should be 4 questions, right? Should be 4 questions, unless Professor Migara did any alterations for the question that I gave. Should be 25 marks. Then that should be 1/4 of the time. That means half an hour per question. That means 2 hours, 4 questions, 25 marks per question. I'll be covering up to the areas that I covered last time. Also, I'm not going to add anything from this time, but last time in the physical lectures. But I did some sort of like a recap of what we did last time, right? Or like a repetition. So don't blame me if you didn't come for the last lecture and say, okay, I came for this lecture. This was today. This was not covered earlier. So you said that whatever was done until last week was coming. So that's not my problem, right? So whatever was done up to the last time will be there. So that should be like the format. I'm not exactly sure whether this is the format. So I think Thilan, you can talk to Cosmicar and see how the. Anyway, I think he was going to take a session to do some questions, right? So you can ask from him exactly the format, but I think it should be 2 hours, 4 questions. That's going to be it, right? So, any other questions? There's another one. Is there a section from state feedback? State feedback. I didn't do state feedback last week, right? So yeah, so state feedback is not there in that case. Or you want state feedback? Easy, no? I mean, few steps, right? Other questions? No? Okay, in that case, we can wind up. You can contact me if you have any questions and doubts. You can obviously, I'll be here, right? You can meet me and clarify if I'm around. If not, you can drop me a mail, WhatsApp, or anything. I don't know. Okay, then we wind up for today. Thanks for coming. I'm sorry that I too had to take 1 day from your study leave for this. And that was basically because I think yesterday was taken by Mr. Madhav. So anyway, yeah. Then that's basically good luck for the exams. And I'll see you all maybe during the exam. Thank you.
Thank you, sir.
Thank you, sir.